All right. The actual mass of the bromine chlorine 35 is equal to this. And so there's no mass defect that we have to worry about. Why? Why don't we have to worry about mass defect in bromine chloride, in the bromine chloride molecule? Why is it just adding up the two atoms' masses work? And so,
The mass defect is already taken into consideration.
I'm sorry?
The mass defect is already taken into consideration when you do something.
Yeah, the mass defect is taken into consideration here. We got the mass defect here, the mass defect here. But that's, to hold it together. But what about holding the bromine and the chlorine? Aren't we going to have another mass defect when we put those? The question is, why not? Electrical forces versus, yeah. Okay, that's the answer. The answer is, when I make a molecule, this is held together by a covalent bond. Covalent bonds are electrical forces, and we don't need the mass defect to overcome the electrical forces in that. And so there is no mass defect. The mass of the atoms comes out, and this is the actual mass. And so there are two ways to determine the mass of a bromine chloride molecule. The two ways, well, actually more, because we have the average. The two ways to determine the bromine chloride mass is, one, just add up the masses of the atoms and make it up. Or two, we could actually put this into a mass spectrometer. When we put it into the mass spectrometer and measure the measured mass should come out as this. And so how precise or how accurate can we get the masses? From well, actually, let me step back a couple of steps. If I want the mass of bromine 79, can I just go ahead and add up the protons plus the neutrons plus the electron masses? Can I just add up the proton, neutrons, and electron masses for bromine 79? Does that work? It's not equal to. If I'm looking at the mass is not equal to this because of the mass defect, right? And so how do I get the mass of a bromine 79? Mass spectrometer. And so the mass spectrometer works. How many sig figs can I get using a mass spectrometer? A lot or a few? Mass spectrometers are capable of giving me a lot of sig figs or just a few sig figs? A lot of sig figs. Mass spectrometers are what we call highly, if you get a lot of sig figs, we call it highly precise or highly accurate, or both, highly accurate and highly precise. Highly precise, good. Just because we have a lot of sig figs, does that mean it's an accurate number? No, you could have a lot of sig figs, which means you have good precision. You spent a lot of money on the instrument, but it can still be inaccurate due to what? Due to errors that contribute to everything. Be more specific. Don't just say errors. Due to not being calibrated correctly. We got to make sure the mass spectrometer is calibrated quickly. And what should we use to calibrate the mass spectrometer? A standard mass, which is a 1U standard mass. Is there such thing as a 1U standard mass? Why not? Is there something that weighs exactly 1 U? Doesn't a proton weigh exactly 1 U? Neutron? Surely you can add up like 400 electrons? No, 200 electrons? Won't 200 electrons weigh exactly 1 U? No, nothing. And so what is the standard mass that I can use to calibrate my mass spectrometer? You have it? Carbon-12, yeah. Good. You can buy a sample of carbon-12. Carbon-12 is actually, in nature, it doesn't occur pure. You know, all the carbon samples in nature are a mix of isotopes. Carbon-12 and carbon-13. Carbon-12 and carbon-13. If you look at that black number, what does a black number under carbon tell us? 12.011. Yeah, that's the weighted average of the isotopes. If there are two isotopes, one is 12, the other is 13, then we see that which one's dominant? 12. Yeah, it's like 99% 12 and less than 1% 13 based on the average there. The average is heavily biased towards 12. Otherwise, the average would be closer to 13 or maybe halfway between 12 and a half. But it doesn't matter because the 13s will hit somewhere else. So you just take a sample of carbon and then you vaporize some of the atoms. And you'll have carbon-12 mostly and some carbon-13. And then in the mass spectrometer, what occurs next? You vaporize those and you have to do something. So now I have neutral carbon-12 and carbon-13 atoms. Let's just focus on the carbon-12. I have neutral carbon-12s. What do I have to do next? You have to ionize it. Why? Because you pass it through a magnetic field, right? Actually accelerated as well, but you pass it through a magnetic field, and if it's neutral species, are they deflected in magnetic fields? No, they just go straight. And so they have to be charged. So you charge it, ionize, we got a positive carbon-12 ion, and that gets deflected. Carbon-12 versus carbon-13, which gets deflected at a higher angle? Carbon-12. Carbon-12 is deflected, and carbon-13 is more massive, so it's not as easily deflected, although the two masses are very similar. You need a very highly precise mass spectrometer to differentiate the two because the masses are kind of close, only 1 U difference, or roughly. And then where the carbon-12 strikes in the mass spectrometer, we're going to call that 12U, exactly 12U, or approximately 12, I should just say two answers. Approximately 12U, or exactly 12U, or how many sig figs do we know that to? The mass of a carbon-12. Shouldn't it be a little under 12? Didn't we say that? Should it be a little under 12? Is it a mass defect? Or is it exactly 12U or under 12U? Exactly 12U. It's exactly 12U. There's still mass defect there, right? Because the sum of the parts is greater than 12. And so some of the mass is converted into nuclear binding energy. Okay, once we do that, we get a lot of digits, right? The modern day mass spectrometers can get 4 decimal places, 5 decimal places, 6 decimal places of precision. As long as it was properly calibrated, instruments working correctly, then it should be pretty accurate as well. Right? And so we got a lot of sig figs. We got a lot of sig figs, so tell me why aren't there so many sig figs in some of these? How many decimal places do we have here for carbon? 3 for nickel. 2 decimal places. Some of these don't even have 1 decimal place. Why? If the mass spectrometer is such a precise and potentially accurate instrument, why aren't there more sig figs in some of these? You know, if they were to cut it off, some periodic tables like to cut it off so it's consistent. In Chem 4, the periodic table went 2 decimal places for everything. Do you guys remember that? But when you look at Petrucci, you know, he has some more, some less. Why? Why not just be consistent? Is it because the average, you know, the rules of sig figs, is that why? Is it because of the mass spectrometer? You know, these guys used an expensive mass spectrometer and these guys used a cheap mass spectrometer. Is that it? And you can see expensive, cheap, super cheap. And this is the discount mass spectrometer that they got somewhere. Is that the reason, you think? No, there's something else. It's not because of the mass. What is it because? What do you think? The average atomic mass, or the weighted average atomic mass, depends on the mass of the isotope. Okay, great. Mass spectrometer, you can get that. Boom, boom, boom. A lot of digits. And what else? So we need to know the mass and something else we get from the mass spectrometer. What is it? Percent natural abundance. And the percent natural abundance is, you know, that's, you just collect samples. You collect samples and measure them, and then you average it to get that. And so sometimes the percent natural abundances can vary depending on where you are. For example, oxygen. Oxygen at sea level is a mix of 3 isotopes, 16, 17, and 18. And you have percentages. Oxygen is mostly 16, as you can see, you know, by the weighted average. It's very close to 16. But as you change altitude, the percent natural abundance changes. So at high altitude, do you know what happens? At high altitude, there's less of the heavier isotopes, more of the lighter. And so as you go up in elevation, the percent oxygen 16 increases, the percent 17 and 18 decrease. At lower elevations, we have more. And so the percent natural abundances can change depending on the origin and where you are, and so you just take an average of those. Although a lot of these, you know, at very high altitude, like ozone, the ozone produced at very high altitude is totally different than the ozone produced in the cities from pollution. The ozone produced from pollution is much richer in 17 and 18 than the ozone produced at high altitude from natural processes. You know, the ozone layer that protects us from the UV. And so there's uncertainties in the isotopic distribution. And so those will be reflected in here in terms of precision. You know, some of the isotopes, how many sig figs do you have in that natural abundance? How many can you have, especially if the spread is wide? You know, there's some variation there. Okay, the other thing that happens is with these. You know, these things are in parentheses for a reason. These are very hard to measure the mass. You know what polonium, radon, you know, some of these have a lot of uncertainty in the average mass. The reason these have a lot of uncertainty is because these are radioactive. And so by the time you spit them into a mass spectrometer, they're already decayed, you know. They're already changed into something else. And so because of the very short lifetimes, they're very hard to measure certain properties. Some things have a very long half-life or lifetime, like uranium. Uranium sticks around for a while, at least a bunch of them will, long enough to measure much more precisely and accurately. Others, just like californium, you know, this lasts like microseconds or milliseconds or something. before a lot of it's decayed. I'm not sure about the exact number, but those are hard to measure, averages. Okay, so for molecules, you know, this is for atoms. For molecules, if we want the mass of the molecule, then it's easy. The mass of the molecule is, for example, we could sum the mass of the atoms in the molecule. Let's just say atomic masses. We could use a mass spectrometer. This is for individual specific molecules, or we could just use the average. You know, the average mass of a molecule is equal to the sum of the average atomic masses. I didn't write it over here. The average mass is very easy because the average mass we just read off the periodic table or calculate it. All right, so the question was, why do we need the masses here? Is it to throw us off? In a way, not really, because they're asking you to sketch, you know, I didn't do this, sketch a mass spectrum for bromine chloride. The biggest peak in the mass spectrum is going to look like this. You know, around 114, this is the 114 mark, but actually it's going to be 113.8872. So a 113.8872 I get a peak right here. The height of this peak corresponds to the percent abundance, whatever that was. I forgot the number, 24% or 25%. Okay. Where are the other peaks going to occur? Well, there's going to be another peak at 116, you know, a little under 116, we're going to have another peak here, another peak here. There are going to be 4 peaks, How do I get 116? How did I get 116? I just did this. Instead of 79, I put 81. And so it's going to be 2 more. It's going to be 116. But that's tricky because this is 116 and this is also 116 when we have a 79 and a 37. But both of these are 116, but I'm not going to get one double-sized peak at 116. This one, you know, if I didn't have the masses, then I wouldn't know. You know, are those 2 peaks one on top of each other, making a double peak, or are they slightly different masses? Both of these are 116 as far as the combined mass number goes, but their masses are going to be different. Actually, let's go ahead and do this since you asked about this one. So if I'm using bromine 81, bromine 81 is 80.9163. And then chlorine 35, we had that earlier. Bromine 79 we had up earlier. Chlorine 37 is 369658. And these 2 masses aren't going to be the same. And so there's going to be 2 peaks very close to one another here, just slightly different in mass. Both of them are going to be below 116. Does that make sense? And so in order to pinpoint this, we need the masses to figure out the actual masses. We can't just use the combined mass number, otherwise that shows one peak right exactly at 116, which isn't the case. You know, I did this because a lot of people have a problem with this. You see, it looks like there's a peak right at 199, so this must be mercury 199, but if you look very closely, do you see the blue line? Does it match exactly with 199? No, it's just slightly lower than 199. So what is the actual mass of that? The actual mass we have to look up. And so the mercury 199, I know what the natural abundance is. Mercury 199 has a natural abundance of 16.84%, but a lot of people, and this is the problem with the book, a lot of people think that the actual mass is 199. The actual mass is not 199. What is the actual mass? The actual mass is actually slightly less than 199 according to this. Look at Mercury 200. When we look at the mass of Mercury 200, it looks like the mass is actually slightly greater than 200. And so we'd have to look those up. Unfortunately, they didn't give them in the book, but these are very common. And they're given in something called the table of isotopes. Sorry, this is not leading to where I want to go. Here it is. This doesn't have the masses either. Okay, maybe I shouldn't have mercury. Let's go to table of isotopes. Okay. Resolution's really bad. Forget it. Anyway, what you do is, where do you find tables of isotopes? We have a book that we have in the lab called the CRC Handbook of Chemistry and Physics. Inside a book like that, you'll find these huge tables of isotopes, so you can find out what the mass is of each of these isotopes and what the percent natural abundance is. They just omitted it from our book to save space, but used to be able to find this a lot easier, but now there's too many tables there. And so we could get that information. And so for right now, I mean, where did they get this mass? Oxygen 16 has a mass of 15.9949. Did they get that from the periodic table? No, what is the mass of oxygen in the periodic table? It's very close. You say 15.9949. What is the mass in the periodic table? 15.9994. 9449. Did they just flip the last two numbers? No, they didn't. No. The mass of oxygen 16 is 15.9949. The average, weighted average of all the isotopes is 15.9994. Just barely a tick above. Why? Because there's just a tiny, tiny bit of oxygen 17 and oxygen 18. Practically all the oxygen that you're breathing right now is oxygen 16. They're going to be light molecules. What's the lightest oxygen, O2, that you just inhaled? How much does that weigh roughly? Roughly 16 U. What's the heaviest oxygen that you just inhaled? Maybe or maybe not inhale. It's 218s. 218s gives you a combined mass number of 36. So the heaviest oxygen is about 36 U. All right, so it depends on how detailed you want. They gave you the numbers so you can make a very detailed mass spectrum, even though they didn't. They should have given you a very detailed mass spectrum where they pinpoint the masses, but they didn't. And so this is why every semester people get confused between mass number and mass. And so this is why I just asked you a whole series of questions about mass number versus actual mass. I would have done it differently. I would have had a very detailed mass spectrum rather than something like this. All right, two more, since I don't want to fall too far behind. We use carbon 12, right? As the standard, as a definition of U. There's both the standard and the definition of the U. You know, we should know what the definition of the U is, right? For example, do you know the definition of 1 kilogram? I know there's a 1 kilogram standard locked away in some vault. I think in Washington, D.C. somewhere. But what is the definition of 1 kilogram? 1 kilogram is exactly what? Yeah, but who figured out what 1,000 grams is? 1,000 grams is exactly what? If somebody, I want to go into the standards business, so I'm going to start making my own 1 kilogram standards and start selling them. How do I figure out how to make a 1 kilogram block of what? How is a 1 kilogram? How's 1 kilogram defined? It's like, this is the same question. How is 1 pound? How is 1 pound defined? You know, who thought of 1 pound and how is that defined? And so I know we have a 1 kilogram standard mass. We can use it. You know, other people can copy it and make their own standard masses. But let's say somebody wanted to define it. You know, how would they do that? And so I don't care. You don't have to know, because you know what? I don't know how 1 kilogram is defined. I should know, but I don't know. But I want you to know the definition of the U, because it's going to be useful for you. Knowing the definition of a kilogram, if you don't know it, you can get by fine. If you don't know the definition of U, it's going to hurt you, because we also have the mole, which is introduced in chapter 2. And so how is a mole defined? What is the definition of a mole? You probably, you know, from Chem 4, you probably don't need to know. Chem 4, you can get by fine without knowing the definition of a mole. Is a mole defined as 6.02 times 10 to the 23rd? Is that it? Is that the mole? 6.02 times 10 to the 23rd is a mole. Avogadro's number? Avogadro's number is a mole. And so there are exactly 6.02 times 10 to the 23rd objects in a mole. True or false? There are exactly 6.02 times 10 to the 23rd objects in a mole. True or false? True? Unfortunately, false. Why is it false? Because that's only 3 sig figs. In Chem 1A, you have to memorize it to 4 sig figs. And so let me rephrase the question. There are exactly 6.022 times 10 to the 23rd objects in a mole. True or false? False. False. See on Wikipedia how many digits. Oh, here we go. I don't know if you could read this. Yeah, you can blow it up. I got it. There are exactly 6.022140857 times 10 to the 23rd objects in a mole. True or false? False. False. Even Wikipedia doesn't have it. Oh, this is interesting. This is news. Changes in the SI unit are proposed that will precisely fix the value of the constant to exactly 6.02214 times 10 to the 23rd. This is a new SI definition. It hasn't been agreed upon yet. And so they want to fix it to exactly that, but they haven't. And so why isn't it exact? Now, if I said this, there are approximately 6.022140857 times 10 to the 23rd objects in a mole. Is that true or false? There are approximately this in a mole. That is true. Why can't I say exactly? Because this number is just an approximation. Approximation of what? What are they trying to approximate? So somebody tell me the definition of a mole. Yeah. They're trying to approximate the number of atoms. That's good. But what atoms and in what? They're trying to approximate the number of these atoms in what? You got to be more specific. Does somebody know? Not in 1 gram. Not the number of atoms in 1 gram. How about if I said this? True or false? There are exactly 1 mole of carbon-12 atoms in 12 grams of carbon-12. True or false? There is exactly 1 mole of carbon-12 atoms in 12 grams of carbon-12. False? That's true. And so this goes to the definition. The reason is this keeps going on. And on. It's like pi. How many digits? You know, I just got a pi poster. The pi poster, they put 6 million digits of pi in there. You have a little magnifying glass, you can read them. I don't know if anybody has those memorized. Probably some guy with some phenomenal, or girl with some phenomenal memory has those memorized. Can you believe that? 6 million. Is that it? Or does it keep going? It keeps going. What about Avogadro's number? It keeps going. There are a lot more digits here. Does it keep going infinitely, or does it stop somewhere? Pi just seems to keep going infinitely, right? But does Avogadro's number keep going infinitely? There's so many more digits you can just tack on one after the other? Or is there a limit where it stops? And then you have Avogadro's number exactly. There's a limit. It should be, you should be able to get Avogadro's number exactly. Just keep going on the digits because of the way it's defined. 1 mole okay, I'll just say there is exactly 1 mole of carbon-12 atom in exactly 12 grams of carbon-12. There are approximately 6.022 times 10 to the 23rd. This number keeps going. Carbon-12 atoms in 12 grams, or 1 mole of carbon-12. And so the mole is defined as the number, the mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. Well, it has different units. I should say a segment later. Okay. So let's ask, why carbon-12? Why not some other atom? Hydrogen. Why didn't they define the mole? We'd get a different number if we said, how many atoms are there in exactly 1 gram of hydrogen-1? In exactly 1 gram of hydrogen-1, do we have 1 mole of atoms? 6.022 times 10 to the 23rd, approximately. We get a different number. And so it depends, you know, since it's carbon-12. Why carbon-12? Because it's related to the U. And so you should know these two definitions, because what we're going to do is we're going to relate the U and the gram. Also, the other reason is it's because of convenience. You know, these masses can be read in 2 ways, which we'll talk about in a minute. But the first thing is the relationship between the atomic mass unit and the gram. By knowing the 2 definitions, we can come up with a relationship, and that is there are 12 U worth of mass in 1 carbon-12 atom. And then using a bit of dimensional analysis, there's 6.022 approximately times 10 to the 23rd carbon-12 atoms in 1 mole of carbon-12. And then there's 1 mole of carbon-12 atoms in exactly 12 grams of carbon-12. So why carbon-12? The carbon-12 comes because of this, you know, the dual relationship. 12 U per carbon-12 or 12 grams per mole of carbon-12. And so numerically they're the same, it's just we're looking at different amounts. Here we're looking at an individual, and so when we're looking at individual atoms, that's U. When we're looking at a mole of atoms, it's going to be in grams, although this is inverted, this is molar mass. We call this molar mass, we call this atomic mass. But we can relate them. The reason I wrote it like this is you can see the relationship between the U and the gram. And that is carbon-12 atoms cancel out carbon-12 atoms. Moles of carbon-12 cancels out moles of carbon-12. 12 cancels out 12. And so we end up with this. Everybody should be able to come up with this conversion factor. There's 6.022 times 10 to the 23rd U in 1 gram. And so there's Avogadro's numbers worth of U in a gram. And so here, here's our relationship between the U and the gram. It's an easy one to remember, to just memorize if you want, but it's also very easy to derive. In case you forget, just use a little bit of dimensional analysis. The book is a little trickier to remember because what they do is they invert this. And so they figure out how many grams are in 1 U. Well, it's like 1.6 times 10 to the minus, I forgot. Very small number. All right, so there's some homework problems. I'm not going to cover very many of them, but some dimensional analysis and some isotope stuff, some natural abundance stuff. Take a look at those homework. If you have any questions on those, ask me. But we're going to move on to chapter 3 next. Chapter 3 deals with compounds. Compounds are 2 or more elements. And the 2 or more elements have to be chemically combined. And so we could have 2 elements, hydrogen and oxygen, forms the compound water, H2O, right? And so how does a compound, H2O, differ from a mixture of hydrogen and oxygen gas? Tell me some of the differences between having a mixture of hydrogen and oxygen gas versus having a compound of hydrogen and oxygen, H2O. And so in other words, compounds are different than mixtures because 1, compounds have fixed composition. Probably the most important. Compounds have fixed composition, but would a hydrogen-oxygen mixture have a fixed composition? No. Those can have variable composition. And therefore the properties vary. And so compounds, but next we're gonna look at the types of compounds we're gonna encounter. The types of compounds are mainly based on the bonds, bond type, and structure. If we have covalent bonds, then typically the compounds that have covalent bonds are going to have molecular structures. Example would be water. H2O. Another example would be CO2. How about SiO2? Silicon is in the same family as carbon. It's right below carbon there. And so CO2 and SiO2, same structure. See, carbon dioxide, silicon dioxide, same structure. Silicon dioxide goes by a common name called quartz. Quartz crystals, silicon dioxide. So quartz and carbon dioxide, same family. Similar properties. Silicon dioxide and quartz. No, totally different. Silicon quartz. For one, carbon dioxide is a gas, quartz is a solid. Not only that, it's a very high melting solid. The same thing happens, carbon. Carbon has what we call different allotropes. Have you heard of allotropes? Same element, but different in a way. So, for example, diamond is made out of pure carbon, and graphite is made out of pure carbon. Since they're both made out of carbon, are they the same? Is diamond and graphite the same? No, totally different. Why? Not because of the composition, because of the structure. And the same thing, the structure of this is totally different. And the structure is what we call network covalent structure. In a network covalent structure, the bonds don't just end, it just keeps going. And we form a network of bonds, or lattice. This is called a lattice. And so it just keeps going and extending out. And so we don't form discrete molecules here. And so the properties of, let's say, diamond are totally different than another allotrope of carbon, which is the buckyball. The buckyball is a molecular form of carbon. And totally different. We have that. Whereas ionic compounds, like this, these are salt crystals here, sodium chloride crystals. If we look at this image of sodium chloride crystals, are there sodium chloride molecules that are found in the crystals here? Do we find sodium chloride molecules? No. No. For ionic, we have the structure that's called an ionic lattice. What an ionic lattice is you just have sodium ions, like this, and chloride ions. But it just doesn't terminate as one sodium chloride molecule. What happens is these charged spheres, these electrical interactions, just continue on and on. And so we build up a three-dimensional lattice like this. And so we don't have a discrete sodium chloride molecule. We have a lattice of sodium ions and chloride ions building up a three-dimensional crystal like this. And they occur in different sizes, big crystals, small crystals, depending on how extensive this lattice extends in each direction. So we got ionic lattices. And so we want to recognize, what type of compound is it? Is it molecular, network covalent, or ionic? Have some idea of the structure. We also have metallic bonds, but the problem with metallic is this. Metallic, you might have something like this, copper and zinc. Makes some brass. So I think brass, is that copper and zinc? Or steel, iron and manganese. So steel. Are these compounds like brass? Is brass a compound? Copper and zinc? No. Brass is what we call a mixture. It's a mixture because, why? Why is brass a mixture and not a compound?
You melt the metal.
Yeah, you melt the two metals together, and the situation with these is you can melt them in different ratios. In other words, you can have variable compositions of brass, variable compositions of steel, None of those are compounds because the composition can be varied, and therefore the properties can be varied. And so metallic, that's the problem with metallic, it's just the way they bond. We don't have a discrete ratio of atoms. So we're going to jump around here. We're going to go from 3.1 to 3.4, 3.5, 3.6, 3.7. 3.4, we deal with oxidation states. Oxidation states, has anyone not assigned oxidation states before? Has everyone's assigned oxidation states? Yes? Good. Oxidation states are very useful for figuring out redox properties. Redox properties, a lot of people say, I don't want to learn oxidation states. I don't want to try to interpret oxidation states because if I need the redox properties of something, and what does redox stand for again? Reduction and oxidation. Do you guys know oil rig? Have you heard of oil rig? Oil is OIL. Oxidation is losing electrons. Reduction is gaining electrons. So oil rig. And so what we're going to do is, since we're trying to figure out, properties based on structure and composition, one of the first things we'll analyze is the oxidation states. And the oxidation states are going to help us understand redox chemistry. So this is why we're going to look at these for the compound. We'll talk a lot more about oxidation states. So for example, did you guys see the explosion in China on YouTube? That was just amazing how powerful those explosions were, right? But apparently, I'm not sure if this is correct, but they're storing calcium carbide there. If they're storing calcium carbide, one of the things you don't want to do is you don't want to spray water on calcium carbide. You spray water on calcium carbide, it makes acetylene, which is a very flammable gas. We use acetylene in welding torches. Or, if you have a metal fire, should you use a CO2 extinguisher? Is it okay to use a CO2 extinguisher on a metal fire? Absolutely not. Why? Well, these things you can read or look up in a book, but if you understand some redox chemistry, you'd understand why you wouldn't use CO2. You would understand a lot more of why you wouldn't spray water on that type of and so redox properties. So we'll be looking at oxidation states this semester. And then we're going to go into organic compounds. So let's finish up talking about organic compounds. A lot of organic compounds are highly flammable. Well, why is that? Well, first, what are organic compounds? Organic compounds are typically carbon and hydrogen-based compounds. They can have other elements, but the backbone of it is carbon and hydrogen. And the reason why, well, carbon's just part of the periodic table, so why, is there a subset of chemistry called organic chemistry that deals with these? And the reason is there's a huge variety of molecules or compounds that have carbon and hydrogen. And the reason is because of the bonding. Carbon is capable of forming 4 bonds, but there's a variety in the bonds. It can form 4 single bonds. It can form 2 single bonds and a double bond. You can form a triple bond and a single bond. So there's a variety of bonding that's observed for carbon. And the other reason is this. Carbon can form chains, extended chains. Some elements don't like forming chains. One element in particular is oxygen. Oxygen doesn't like to form chains. In fact, if we compare this to oxygen, this type of bond is called a peroxide bond. And it's very unstable. And so oxygen really does not like to form chains of single bonds. Here, this is okay. This is okay, but once you form the double bond, you aren't going to form any other bonds. This. But carbon is no problem. This is stable. That being the case, you can form short chains or you can form very, very long chains. Not only chains, but branches, etc. Rings. And so because of this, there's a huge number of compounds, but they all behave, according to electrical forces being most important in chemistry. So they behave like anything else. It's just a subset of chemistry called organic chemistry. We do this. Now, looking at the chains, we're going to talk about nomenclature. And so if we have one carbon, it gets the base or the parent name, meth. Two carbons in a chain gets the F. 3 prop. 4, and they don't have to be all straight in the line. They could go down or up or whatever, zigzag. This is bute. Let me just finish off with this real quick. 5 is pent. So it can go like this. Just the longest continuous chain, no matter where it goes. 6 this is hex. 7 is hep. 8 is oct. 9 is nona. 10 is dec. Nona. We go what, until 3:25? Yeah, so I fell behind a little bit. Questions. So I'll continue this Wednesday.